be strong.
Hey everyone, welcome to InDepth Academy. This is the second session of the series straight from the book Grade 10 Mathematics, and this is the second part of the chapter Real Numbers, Grade 10. So in this we are going to cover the examples from section 1.2. In the previous session we covered section 1.2, which showed us the fundamental theorem of arithmetic. So in this session we'll go through the examples. The examples are a little twisted, and these show you the application of fundamental theorem of arithmetic. It's not like you always learn the theory and not the application. So here you're going to learn the application. Consider the numbers 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. Now for suppose we can say x to the power n ends with the digit 0. Then x, this is the condition. So x should have minimum 1, 2 and 1, 5 as prime factors. So if this is a minimal requirement to be met for any of its powers to end with 0. For example, 5 2s are 10. We can take 10 to the power n. So 10 to the power 1, 10. 10 to the power 2, 100. 10 to the power 3000. All of them end with the digit 0. Suppose you take 20. 20 to the power 1, 20. 20 to the power 2, 400. 20 to the power 3, 8000. All of them end with the digit 0. What is common in all of them? 2 into 5. 2 and 5 are common prime factors in all of them. So when you are taking 4 to the power n, 4 to the power n is equal to 2 square whole to the power n, and by using the identity that a to the power b whole to the power c is equal to a to the power b into c. I've just used random variables here, but yeah. So using that identity, 2 to the power 2n. So here 2 is the only prime factor of the base and 5 is not. So hence 4 to the power n for any natural number n cannot end with 0. Let's see what answer they have given. If the number 4 to the power n for any n were to end with the digit 0, then it would be divisible by 5. Since 5 should be its prime factor, we just discussed. That is, the prime factorization of 4 to the power n would contain the prime 5. This is not possible because 4 to the power n is equal to 2 to the power 2n. So the only prime in the factorization of 4 to the power n is 2. So the uniqueness of the fundamental theorem of arithmetic guarantees, see, the uniqueness of fundamental theorem of arithmetic. It guarantees that there are no other primes in the factorization 4 to the power n. The only prime is 2, the only prime is 2. There can't be any other prime in the factorization. If n is 1, 4 to the power 1 is 4. So 2 is the only prime factor. 4 to the power 2, 16. 2 is the only prime factor. 4 to the power 3. So how you can keep going and you'll keep finding that 2 is the only prime factor. So there is no natural number n for which 4 to the power n ends with the digit 0. Next, you have already learned how to find the HCF and LCM of two positive integers using the fundamental theorem of arithmetic in earlier classes without realizing it. This is called prime factorization method. We had learned prime factorization method in the previous classes, if you can recall. So through an example, we'll be recalling this again. Right? So find the LCM and HCF of 6 and 20 by prime factorization method. So first we need to factorize. 6 can be written as 2 into 3. This is in terms of product of primes. In terms of product of powers of primes, you need to write the exponent as well. Now 20 can be written as 2 into 2 into 5, which can also be written as 2 square into 5. Now if you write it in terms of primes, you can easily find the HCF, and terms of powers of primes, you can easily find the LCM. So that's the reason it's being written like this. So you need to find the HCF and LCM. To find the HCF, we need to look at what's common. So 2 is common in both 6 and 20. So HCF, only 2 is common. So HCF of 6 and 20 is 2, and LCM of 6 and 20, since you need to use prime factorization method, the highest powers of all involved primes. So here 2, 3 and 5 are the involved primes. Highest powers 2 square, 3 to the power 1 and 5 to the power 1. So this can be written as 2 square into 3 into 5, which can be written as 4 3s are 12, 12 5s are 60. So the LCM is 60 while the HCF is 2. Now we need to verify this. So how do you get it verified? To verify, there is a very simple rule. LCM of A and B into HCF of A and B is equal to the product. So this equation helps us verify whether our results are right. Now A and B are the two numbers. LCM is their LCM, HCF is their HCF. So we got the LCM to be 60 and we got the HCF to be 2, and the first number was 6 and the second number was 20. If you multiply them, 120 on the LHS and 120 on the RHS, so LHS is equal to RHS, and hence our solution is correct. This is how it must be verified. The next one, find the HCF of 96 and 404 by prime factorization method, hence find their LCM. Now you need to find HCF, so you can just write it in terms of products of primes. So you can write it as 2 into 2 into 2 into 2, sorry for the disturbance, 2 into 3, and 404 can be written as 2 into 2 into 101. So to find the HCF, you need to find what all are common. So 2 and 2 are common in both 96 and 404. So HCF of 96 and 404 is equal to 2 into 2, which is equal to 4. So 4 is the highest common factor of 96 and 404. Now to find the LCM, we know that you'll have to write LCM of, like in the bracket also. I'm just writing this because it's difficult to keep writing. You know this. But at the same time, this implies that LCM, when you divide both LHS and RHS by HCF, you get LCM is equal to AB divided by HCF. Agreed? So what is A? 96. And what is B? 404. So and what is the HCF? HCF is 4. So 96 into 404 divided by 4. Now 404 divided by 4 is 101. 96 into 101 is equal to 9696, and this should be your LCM. So yeah, 9696 is LCM and HCF is 4. That's our result. Next, find the HCF and LCM of 6, 7 and 120 using prime factorization method. Now in this, one thing to be careful is that HCF into LCM is equal to product of the numbers. That is only applicable when there are two numbers given, not when there are more than two numbers. So here there are three numbers, so you cannot use LCM into HCF rule. So we have to find them only using prime factorization method, and that's the reason they've even specified using prime factorization method. So first we need to factorize. 6 is equal to 2 into 3. 72 is equal to 2 into 2 into 2 into 3 into 3. That's basically 8 into 9. 2 cube into 3 square. And 120 is equal to 2 into 2 into 2 into 3 into 5, which can, again I'm sorry for the disturbance, can't be helped, 2 cube into 3 into 5. So what is, to find the HCF you need to find what is common. So what is common? 2 into 3 is common everywhere in all three numbers. So HCF becomes 2 into 3, which is 6. So the HCF is 6, while the LCM is, to find the LCM, highest power of all involved primes. So 2, 3 and 5 are the involved primes. highest power of 2 is 2 cube, 3 is 3 square, and 5 is 5. So LCM becomes 2 cube into 3 square into 5. 2 cube into 3 square is nothing but 72. 72 into 5 makes it 360. So the HCF is 6 and the LCM is 360. Can we confirm that? Yep, HCF is 6 and LCM is 360. So with this, we're done with the examples from section 1.2. In the next session, we're going to cover the exercises, exercise 1.1. Thank you so much for watching. Hope you had something to take away. Thank you. Have a good day.